Okay, welcome back to our subject, reinforced concrete design. And for this session, we will now proceed with the design of concrete flange sections or design ng T-beams natin. All right, so as I recall, we have here the provision from NSCP on how to determine yung effective width ng flange na gagamitin natin for the estimation of the effective width na kino-consider for the design of T-beams. We also discussed yung two types of T-beam, which is yung rectangular T-beam and true T-beam, wherein yung rectangular T-beam is yung neutral axis natin is within nung flanges natin, yung slab natin. And then when the neutral axis is beyond or below the bottom of the flange, meaning a portion of our compression block is um, already at the location of the web, so that is considered as true T-beam. And we have already discussed how to analyze the forces when it comes to true T-beam. Then we stated here are the steps for the analysis of T-beams. Okay, and from this step we can utilize some of it in determining the procedures for design. For design, first thing is we have to assume that our T-beam is a rectangular T-beam. It means that um, the neutral axis fall within the flange. Therefore, the value of our B in this equation for the row will be the base of the flange. And then right after we have a value for a row, we can determine the value of A using this formula. And then we can compare with our height of slab. Remember that the height of the slab is already identified or known section, known dimension, or based from the minimum thickness requirement of the code when we have discussed one-way slab. Okay, so as previously stated, if it's less than or equal to the height of the slab, we consider the T-beam as rectangular T-beam, otherwise it's true T-beam. Okay, then we say that if it's a rectangular T-beam, the sign will be as we have done in rectangular beams. And if it's a true T-beam, we utilize a simplification. So this simplification is based from the second method that we have discussed previously on the analysis of T-beam, wherein we try to decompose the original T-beam section into two sections, wherein the first one, ang shown is yung critical portion for the flanges, and then the other portion is the web. Okay, then um, we derive a formula for the moment or the value of the compression forces of each section. Here we call this as the compression for web, and then this is the compression for the flange. So after splitting the T-beam, we can have the force, this is CF, then multiplied by the moment arm, and then also for the CW and the moment arm. Adding these two will yield with the nominal moment capacity of our section and will determine the number of rebars we need for the given um, properties of the T-beam to be designed. Okay, so as a general procedure, here's the order of procedures. Number one is to compute for the factored moment. Because we are designing, we try to check what is the ultimate load that we expect the T-beam to be, that the T-beam will carry. So using the known dimensions and the given distributed load or superimposed load, dead load, and live load, and self weight of the beam, we can identify the value of the ultimate moment. Next, after having the value for the ultimate moment, we assume that the section is a tension controlled section, so we assume phi is equals to zero point 0.9. So using mn is equals to mu over phi, we were able to get the value or the equation for mn, for the value for mn. And then we can now get the value for phi. So assuming that first that the neutral axis is in the flange or within the flange, it means that the b that we will use here is the width of the flange. If the width of the flange is not given in the problem, we will use or utilize the table that we have discussed prior and identify the minimum width that is considered as our effective width. Next, after that, we compare or we calculate the value of A using this formula. And then once that the value of A is less than or equal to HF, we treat it as a rectangular T-beam, and we will proceed to the fifth step. If not or otherwise, it means that the neutral axis is in the web, so we go to step 8. So first, once we prove that the T-beam is a rectangular T-beam, we use this process. So we use AS required is equals to PBD, and then we can use our design A table from our previous lectures to identify the number of rebars adequate for our section. And then we will try to check for the NSAP requirement, meaning for the minimum reinforcement, if we have provided the minimum required, and then also to check if the prior assumption, which is a tension controlled member, suffice. If not, another value of phi should be calculated, but it should be noted that for a T-beam section, the steel will always yield, meaning the strain is always greater than our ATY or 0.0024 for grade 60 or 420 megapascal rebars. Okay, and then for if our T-beam is a true T-beam, we proceed with the calculation of the first portion of our decomposed section. So we try to identify the area required for the flanges. So we use the formula T is equals to C. Okay, wherein C is about the compression of the flange, that is 0.85 F prime C, BF minus BW. And to get the area, we know that T is equals to AS Fy. So if we need AS, we just divide both sides by Fy. Hence this formula. Then after getting the value of the area, we can calculate now the value of the moment using this formula. Once we have the value of the moment, we now have the quantity for the flanges. The unknown now is the remaining moment capacity needed to be supported by the web. So from our ultimate moment, we subtract the ultimate moment of the flanges all over phi or our resistance factor. So far it's zero point 0.9. And then we will have our value for Mn. Once we have our Mn, we will use the formula for rho to calculate for the value of rho. But take note of the value of B since we are now considering the web portion of our decomposed sections. The B value should be BW. And then we will now be able to calculate ASW. And lastly, we can now determine the area required for of the section by adding the area required on the flanges and area required of the web. Then upon having the value of AS, we will now choose a reinforcement pattern efficient for our section, and then we will check NSCP requirements if it adheres to the minimum area requirement and also the um, the first assumption that the steel section controls. Okay, so let's solve two design problems. to better understand the steps that we have discussed. Okay, for the first one, design the reinforcement for the T-beam shown. We have F prime C is equals to 28, Fy is 420. Length of the beam is 6 meters. We have a superposed dead load of 15 kilonewton meters. We have live load of 30 kilonewton meters. So for the floor system, we have S, or the center to center spacing of the web, equals to 3 meters. We have beam width is 300. Height of flange or slab is 100. Effective depth is 450. Then H is 525. Okay. So first step that we need to do is to calculate for the ultimate moment. To calculate the moment, we need the value of the dead load and live load. For the dead load, the one given is SDL lang. So kulang pa siya ng self-weight niya. So we need to calculate yung self-weight ng T-beam natin. So let's say we are considering this T-beam. Okay? So what do you think we can do to calculate for the self-weight of this beam? Do we need to consider BF only? No? So we have to be aware na itong mga T-beam natin, may mga portions siya na kailangan i-carry. And this portion is what we call yung mga tributary width na kinoconsider natin. Okay? So meaning yung gitnang T-beam natin, ito yung width or tributary width na kinoconsider niya. Meaning ito yung width na kine-carry niya, na pumupunta sa kanya yung loading na yan. Okay? The other portion, bawa itong remaining ng flange na to, will be carried by this T-beam, and then this portion will be carried by this T-beam. Okay? So yung tributary width, different siya do sa effective width ng flange. So effective width ng flange, nagmamatter siya do sa stress distribution natin. Okay? Pero pag gusto natin ma-identify yung tributary width o yung yung nakapatong mismo sa ating T-beam, we need to get our um, tributary width. Okay, so let's call this WT or TW para hindi tayo confusing. Okay, so kung i-carry niya yan, so yung half nitong portion na to, so that is S over 2. So S over 2 is 1.5. So this is 1.5. Then the other side, 1.5. Meaning, 3 meters yung tributary width natin. Okay? So meaning, yung ating mga loadings, ito yun, ano? Yan, ito yung kailangan nating ipakarga do sa T-beam natin. Okay? So, nandyan yung ating um, superposed dead load, live load, and self-weight. So, for the self-weight, you can calculate yung self-weight by using yung formula na self-weight is equals to gamma ng concrete or yung unit weight ng concrete. So, hindi given. So, assume natin na 24 kilonewton per cubic meter multiplied by the area of concrete. So, yung area ng concrete na consider natin is, syempre, itong portion na to. No? Okay? And we can utilize yung halimbawa, i-subdivide natin ng 2 section para madaling makalculate yung area niya. No? So, unit weight sa 24 kilonewton per cubic meter times yung area muna ng flange natin. That is yung ating tributary width na 3 meters times yung thickness niya which is 0.1 meters. So, ito yung ating flange, and then for our web, that will be yung width natin is 0.3 meters. And then yung height natin will be yung ating total height, which is yung H natin, minus yung base ng flange. So that is 0.525 minus 0.1 meters. Okay? So yung ating self-weight will be, so how much? So we have 24 times 3 times 0.1 plus 0.3, 0.525 minus zero point 0.1. So we have 10.26 kilonewton per meter. Okay. Then to calculate for our moment, our ultimate uniformly distributed load will be 1.2 times WDL, dead load, plus WLL. For dead load, that will be the combination of our self-weight and yung ating SDL, 1.2 times 10.26 plus 15 kilonewton per meter to ha. Then, for live load, sorry, may multiplier tayo. So, 1.6 WLL. So, 1.6, 30. Okay? WU is 1.2, 10.26 plus 15 plus 1.6 times 30. We have 78.312 kilonewton per meter. So to get the moment, we assume simply supported, WL squared over 8. So we have 78.312 times 6.0 squared all over 8 is equals to 352.404 kilonewton meter. So this is our value of moment. Ito yung i-carry ng T-beam natin. And this is where our design will be based upon. Okay? Next. Okay? So, next step is to identify our MN. So that is just MU over phi assuming nag-tension control tayo. So 352.404 kilonewton per meter all over zero point 0.9 will be 391.56 kilonewton meter. Okay. Next, step 3 is to get the value of phi using 0.85 F prime C over Fy times 1 minus square root of 1 minus 2mn all over 0.85 F prime C B. Since assume natin na um, rectangular muna siya, BF muna yan, D squared. Okay? So that is 0.85 times 21 over 420. So we have 1 minus 2 times 391.56 convert into Newton mm, kaya times 1 million, over 0.85 times 21 times BF. Wala pa tayong BF. So, let's calculate BF pala. So, according to our formula, BF is equals to minimum between BW plus 16HF SW or ln over 4. So this is um, how much yung BW natin? BW is 300. Okay? So 300 plus 16 times 100. So that is 1,900. SW is 3,000. ln over 4 is 6,000 divide 4 or 1,500. Okay? So whichever is minimum, therefore, BF is 15 mm. Okay? So 15 times ang ating D is based from our equation that is for figure 450 squared. Okay? So rho is equals to 0.85, 21, 420, 1 minus square root of 1, 2 times 391.56 times 10 to the 6, 0.85, 21, 15, 450 squared. So 0.00319 Next, we have A is equals to rho FYD over 0.85 F prime C. So we have 0.00319, 420, 450 over 0.85, 21, 28. I'm using 21 pala. So 28 tayo, 28, sorry. So mag-iiba yung value, no? So this is 28. Okay, for a while. 28. That is 0.00316. Okay, this should be 21. 28. So we have 420, 450 divide 0.8528. That is 25.072 mm, which is less than nung ating height nung flange. Therefore, siya ay within the flange. And ano nga pag within the flange? Within the flange, therefore, siya ay rectangular T-beam. Okay? So, kung rectangular T-beam siya, continue tayo as is, no? So, ibig sabihin, as parang beam na yung consideration natin sa kanya. So, AS is equals to rho BD. Yung rho natin is 0.00316. So, yung base natin dito is yung ating BF kasi yan yung portion, yung flange natin. And then, 450. We have AS is equals to 0.0031615 450. Okay, 2133 mm squared. So let's look at our design aid on how many number of rebars are needed to have 2133. Okay, so this is our design aid. So let's see. Um, if we try to use 28 mm, 4 pieces will suffice, no? 2, 4 to. 2, 1 lang yung kailangan natin. 2, 4 to. So let's check kung ilan ng 4 pieces na 28. So with 4 pieces na 28. 4 pieces na 28, ang required width natin is 308. Pero ano ba ang width ng flange na ng web natin? Ang width ng web natin is 300, no? So hindi pwede ang diameter 28. Hindi siya kasya, ibig sabihin. So let's go dun sa 32. Let's try 32. So 32, how many pieces ni 32 ang kailangan natin? Kung 32, yan, 3 pieces. Let's try 3 pieces. 2, 4, 1, 2 yung area niya. So pasok dun sa required area natin. 3 pieces na 32. And tingnan natin, pag 3 pieces na 32, ang required na width niya ay minimum 268. 300 yung atin. So pasok siya yung width. And then, yung area natin is 2, 4, 1, 2. Okay? So, use diameter 32. 3 pieces ng diameter 32. Ang AS niya is 2412 mm squared. Okay? So, once na meron na tayo niyan, i-check na natin yung kanyang adequacy ano, doon sa NSCP requirement natin or kunin natin yung A. So, A is equals to AS FY over 0.85 F prime C. Again, yung B natin dito, since rectangular TB ang assumption natin, BF to. Okay? F prime C, BF. Okay. So we have 2412 times 420 all over 0.85. F prime C is 28. Then we have 1,500. So that is 2412, 420, or 0.85, 2815. We have 28.376 mm, which is indeed less than dun sa height ng flange natin. Therefore, okay. Okay? Then C, we have A over beta 1. Since our F prime C is 28, so beta 1 is 0.75, 0.85 rather. Okay? So 33.384 mm. Our strain will be 0.003 D minus C over C. Substituting the value, 0.003. We have 450 minus answer over answer. That is this correct? Point. Our D is 450. So 0.0374, which is greater than do sa ETY natin na 0.002 for grade 60 and limit natin na 0.005. Therefore, yung fee natin gagamitin is 0.9 or assumption is correct based from our second step. Okay? Next is calculating our moment capacity. So Mn is equals to As Fy d minus A over 2. So that is our provided area. So this is our area provided, no? So 2412 times 420 times 450 minus 28.376 over 2. So Mn is 2412 times 420 times 450 minus 28.376 over 2. So we have divide natin by 1 million to make it kilonewton meter unit. We have 441.9495 kilonewton meter. Okay? So ang kailangan natin is Vmn. So 0.9 of our Mn. So that is times 0.9. We have 397.345 kilonewton meter. Okay? So, yan yung capacity ng provided reinforcement natin. So, let's check efficiency. MU over VMN. So, ating MU is based from our first step, 352.404. Sorry. Okay, so we have 352.404 divided by 397.345 times 100. Our efficiency is 404 divide answer times 100. 88.69%. Okay, which is okay. Okay, checking for AS mean. AS minimum is equals to BWD over FY times maximum between 0.25 of F prime C tsaka 1.4. So that is BW natin is 300, D is 450, Fy is 420 times pag sinubstitute nyo yung 0.25 F prime C mas greater than si 1.4, no? So AS minimum 450 over 420, that is 32 times 1.4, 450 mm squared, which is less than dun sa area provided. Therefore, okay. Okay? So use 3 diameter 32 mm rebar. So that is our designed number of reinforcement adequate to support the given loadings. Okay? So, right after natin makuha yung area, nag-checking agad tayo, no? Chinek natin kung yung assumption is correct. And then, kinuha natin yung ES minimum. And then, verify lang natin yung efficiency ng suction natin. Meaning, gaano ka layo do sa required na capacity, yung capacity na kuha natin, which is 88.69 is not very bad, no? Nasa economic side tayo. Okay? So that is for the first example. Next, we try another one. So yung first example is a rectangular T-beam. So let's hope yung second one is a true T-beam. Then we can demonstrate how can we design if naging true T-beam naman siya. Okay, so we have here design the reinforcement for the T-beam shown. We have F prime C is 21, Fy is 420, Mu is 1,200 kilonewton meter, included na yung self-weight niya. We have a width ng flange is 1,350, height ng flange is 75, and ang effective width natin is 600 and BW natin ay 375. Okay? So, yung first step natin is to identify yung MU. Fortunately, this problem, given naman siya. So, proceed na tayo sa step 2. Step 2 is using MN, assuming nag-yield o tension controlled. So, 1, 2 over 0.9. That is 133.33 kilonewton meter. Okay? Number 3, we calculate the value of rho. So that is 0.85 F prime C over Fy 1 minus square root of 1 minus 2mn 0.85 F prime C. Assumption is rectangular tibia muna siya at first. So D squared. So kayo na lang yung mag-substitute tong values, no? I will directly go to our calculator. 420 times 1 minus square root of 1 minus 2 times 133.33 times 10 to the 6. 0.85 times 21 times BF natin is given 1,350. D natin is 600 squared. Okay? So we have 0.00713. So next is ating A. So rho Fy D over 0.85 F prime C. 713,420 times 600 all over 0.85 times 28. 0.00713 times 420 times 600 over 0.85. Sorry, 21. 21. Okay, so that is 100.659 mm, which is greater than dun sa HF natin. Therefore, it means na yung NA natin is below nung flange. Then, meaning, true T-beam tayo. Okay? So, true T-beam tayo. Okay? Let's proceed. Kung true T-beam tayo, so, i-divide natin sa dalawang section yung ating T-beam, no? So, let's say, ito yung first section. Copy lang natin. Yan. So, ito yung T-beam natin. Okay? So, halimbawa, using yung method. Sige. Gawin natin dalawang method. Gawin natin yung first method. Ibig sabihin, yung first method natin sa analysis. First method dito. So, we have identified na, no, na somewhere dito yung ano natin, yung compression natin. Meaning, itong portion na yan yung ating compression block. Okay? So, to identify AC, so we have, pwede natin calculate yung what we have here is yung ating pro. Okay. And then, proceed tayo dun sa ASF kasi true T-beam na nga pa tayo. So, step 8 tayo. So, true T-beam. So, step 8, doon sa procedure natin is to calculate for ASF. That is 0.85 F prime C BF minus BW HF all over FY. Okay? Substitute, we have 0.85 times 21 times 1,350 minus 375 times 75 all over 420. ASF is 0.85, 21, 1,350 minus 375, 75 over 420. Okay, so this is 3107.8125 mm squared. Okay, then get yung moment capacity niyan. So we have ASF times Fy times D minus HF over 2. So direct substitute ko na lang 420 times D is 600 600 minus 75 over 2. So we have a moment capacity of 734.221 kilonewton meter. Right to 1 million. Okay? So ito is step 5, step 8. 9 is to get yung ating MNW using MU minus phi MNF all over phi. Okay, so MU natin is 1,200 minus 0.9 of 734.221 all over phi. So MNW is equals to 599.113 kilonewton meter. Okay, now we have that, we can calculate yung ating rho using 0.85 F prime C Fy 1 minus square root of 1 minus 2 Mn 0 and MNW 0.85 F prime C BW D squared. So rho W is 21,420 times 1 minus square root of 1 minus 2 times 599.113 times 10 to the 6 all over 0.85 21 375 600 squared. So that is 0.0124. Okay? So yung ASW is PBD. So that is 0.0124 times 375 times yung 600. So ASW is 2782.160 mm squared. Okay? So yung ating total reinforcement needed is ASF plus ASW. So that is 3107.825 plus 2782.160 mm squared. Okay? AST is equals to 8125. Okay, so 5889.973 mm squared. So ito yung kailangan natin, ano? Na area na support na lagyan ng reinforcement o yung total area natin. So tingin tayo doon sa table natin, again. So kailangan natin ng 5 at least 5.8 o 5.9, ano? So ang 5.9 natin is around dito, no? Meron tayong 8 pieces na 32. Okay? And then, sa 36, pwede yung 6 pieces na 36. Okay, 6 pieces na 36. Pag 28 kasi, 28 na 11 pieces. Okay? Tingnan muna natin ito sa 32. Ang 8 pieces na 32, yan na yung width na kailangan niya. Ibig sabihin, no? Pag 8 pieces tapos 32, ang width na kailangan natin, minimum ay 588. Ay 375 lang yung width natin. So, hindi pwedeng isang layer lang yung ating reinforcement. Ang pwede natin gawin, yung 832 natin, pwede nating i-divide sa 2 layers. So, pwedeng maging 4 pieces sa isang layer, 4 pieces sa kabilang layer. So, minimum ng 4 pieces na 32 ay 332. So, papasok siya doon sa 375 na requirement natin. Okay? So, gamitin natin, try 8 na diameter 32. Ang kanyang AS is 6432. Okay? So, ibig sabihin yan, pag ito yung ating rebar, yan, yan, ganyan yung reinforcement natin. Then, nandito yung effective depth natin. Okay? Sa centroid nung layers natin. Okay. Now we check kung ano yung magiging capacity nung pinrovide nating AS. Okay? So, yung pag-check ng capacity, we can use yung second ano natin. O yung first pwede din. Okay? So, tayo muna natin yung second one. So, halimbawa, meron na tayo nung sections natin, ano? So, ito yon plus another nyan. Okay? So, yung first natin section is ito. Okay? Yung another section is ito. Okay? So, ito is BF, BW, HF, then ito is yung ating A, then BW. Okay? So, para makuha si A na kailangan natin, yung value ng A. So, pwedeng yung total reinforcement natin is equal sa CF plus CW. So, that is ASFY. So, 6432 times 420 plus 0.8 equals yung 0.85, 21, 1350 minus 375 times yung height ng flange na 75, okay? Plus 0.85, 21. Width natin na 375 times yung A na unknown. So A is 6432, 420 minus 0.85 times 21, 1350 minus 375 over 75. Divide that by 0.85, 21, 375. Ang A natin is 208.576 mm. Okay? So, that is greater than doon sa HF natin. So, therefore, okay, T-beam talaga tayo, no? So, C natin is A over beta 1. So, that is 245.384. So, yung ating strain is 0.003. That is 600 minus answer over answer. That is 0.004335. Hindi, greater than siya sa TY natin. Ibig sabihin, still yields. Pero siya ay, hindi siya greater than sa limit natin. So siya ay transition zone. Okay? So dapat yung phi natin is 0.65 plus 0.25 multiplied by ET minus ETY minus E limit minus ETY. Okay, so that is 0.65 plus 0.25. That is 0.004335 minus 0.002 all over 0.003. Okay, pag kinalculate lang, phi is equals to, diretso ko na, 0.25 times points, 0.004335 minus 0.002 over, kaya naging 0.003 is 0.005 minus 0.002. Okay? That is 0.845. So, yan yung gagamitin nating phi pag-calculate ng moment natin. Okay? So, pag-calculate ng moment, gamitin lang natin yung moment is equals to yung formula natin ng CF is D minus HF over 2 plus CW D minus A over 2. Okay? So that is 0.85 F prime C BF minus BW times D minus HF over 2 plus 0.85 F prime C then BW times A times D minus A over 2. So substituting yung values na nakuha natin sa previous slide, 21 times 1,350 minus 375 times 600 minus 75 over 2 plus 0.85 times 21 times 375 and ang value ng A natin is 208.576 times 600 minus 208.576 over 2. Okay? And then divide natin both whole equation by 1 million. So yung ating value, wait lang, let me check. 1,350, 375. May kulang dito, no? Yung height ng flange. Height ng flange. Okay? Height ng flange is 75. Okay? So 1426.312 kilonewton meter. So yung VMN natin, using yung value na 0.845, 26.312 kilonewton meter. So VMN natin, so 1205.233 kilonewton meter. Okay? So efficiency natin is MU over VMN. So that is 1,200 divide 1205.233 times 100. Efficiency natin is equals to 99.57%. Okay? So, medyo sagaran siya, no? Pero, that's okay. At least pasado pa din siya, no? AS minimum natin, so that is BW D over Fy times max between 0.25 square root of F prime C over or 1.4. So we have 575, 375, 600, 420 times ang mas malaki is yung 1.4. So that is 375, 600, 420 times 1.4. That is 750 mm squared. AS mean is less than dun sa A provided natin. Therefore, okay. So, use 8 pieces na diameter, 32 mm. Okay? So, yun. Pero, kailangan lagay natin na siya ay 2 layers pala. Okay? So, ayan. Ganyan po yung isang method ng pag-check, no? After mo makuha yung A provided mo, yung pag-check mo ng capacity. Okay? So ito yung sa second method. Yung first method, pwede din naman, ano? Okay? So, di ba? Nakuha natin yung A provided natin, that is 6432. Okay? Pwedeng gawin natin, kunin natin yung AC using yung ASFY over 0.85 F prime C. So that is 6432 420 all over 0.85 times 21, 0.85 times 21. So that is 151,341.1765 mm squared. Ito yung ating area ng compression block. Next is yung area ng flange. Area ng flange is just HF times BF. So that is 1350 times 75. So 1350, 75. So 101,250 mm squared. So greater than sa AC, since less than kay AC, um, through TTB, ano, through T-beam. Okay? So yung area ng web naman, okay? Area ng compression minus area ng flange. So makukuha natin 151,341.1765 minus yung area ni flange. Remaining is 50091.1765 mm squared. So ano ba yung magiging figure niyan? Yung figure niyan ay ganito, no? Ito yan. Ito yung area ng flange. Area ng web is ito. Okay? So ito yung sa area ng flange. Ito yung sa area ng web. Okay? Alam natin na itong portion na to is 75, yung HF natin. Ito yung hindi natin alam. So, tawagin nating Y. Okay? O Y1. Okay? Para makuha si Y1, AW is equals to, ito is BW. Area ng web ay equal sa width times height. So that is BW times Y1. So Y1 is equals to AW BW. So that is yung 50091.1765. Divide natin ng 375. So divide 375. We have 133.576 mm. So para makuha yung ito, depth ng compression block, that is A. That is 75 plus Y1 is equals to 208.576 mm. Which is the same na nitong nasa taas. Nasa kabilang slide pala. So 208.576. So ibig sabihin pag chinek natin yung strain, same strain yung makukuha natin, 0.845. Okay? So lagay lang natin dito, strain is 0.845. So ngayon ang calculate natin is yung moment. Okay? So kung ito yung reinforcement, yung load natin at T is ito. Yung C niya is somewhere dito. Kanyang C. So meron siya ditong moment arm na Z. Ang Z ay equal sa D minus yung distance na to. Tawagin nating centroid nung compression block. Okay? So paano makukuha yung bar Y? So bar Y, siguro barig nons tayo, area nung flange which is 101,250 tapos yung distance ng centroid niya pataas at is 75 over 2 plus yung area ng web which is 50,091.1765 times yung distance, so that is 75 plus yung value ng A over nung Y bar Y1, lagyan natin dito. Okay. Times 75 plus 133.576 divide 2. Okay? Bar Y. Tapos divide natin dun sa area ng concrete which is 151 341.1765. So bar y is equals to 101 to 50, 75 over 2 plus 50,000, 91.1765 times 75 plus 133.576 over 2 plus divided by the AC 151,341.1765. We have 72.017 mm. So yung D natin dito will be 600 minus 72.017 mm. Z is equals to 527.983 mm. So, para makuha si Mn, that is just moment ni T times yung Z natin. So, that is ASFY times Z natin na 527.983. Okay? So, this is 6,432, 420, 527.983. Mn is 1426.314 kilonewton meter. Divide ng 1 million to. VMN, so 0.845 mn. So VMN, so 1205.236 kilonewton meter. Okay? Which is, I think, the same nung nasa taas. May konting discrepancy lang due to rounding of numbers. Pero same method are acceptable to calculate for the moment capacity. Okay? So matter of kung paano nyo siya i-did sa subdivide, kung saan kayo mas madadalian ay identify yung mga lever arm natin for the moment nung forces natin. Okay? So, once you have this, pwede mong compare ulit dito sa efficiency, then you will have the same answer, then we'll check the AS minimum, and then our answer is the same. Okay? So, ayan. So, regarding naman dito, no? Since hindi naman given yung height nung T-beam natin, no? So pwedeng idadagdag since magdadalawa na yung layer niya, okay? Dagdagan na lang natin yung concrete cover niya dito sa ilalim. As long as yung effective depth should be located dun sa center nung layers natin or kung nasaan yung ating centroid nung layers na ipoprovide natin. Okay? So, ayan, that's it for design of T-beams. I hope naintindihan siya. Then next session, we will proceed with the analysis and design of doubly reinforcement beams. So same concept halos nitong T-beams. Papakita lang natin kung paano kino-consider yung pag-yield or pag-not yield ng compression steel natin on the compression side of our beam. Okay? So thank you for listening. Goodbye for now.